learn about enzyme kinetics and how they're affected by inhibitors. Inhibitors work by reducing the efficiency of the enzyme. Inhibitors can be good if they inhibit, good drugs if they inhibit bacterial or viral enzymes. They can fall into 3 different classes of inhibitor: competitive, uncompetitive, or mixed, and can either be reversible or irreversible binders. The first type of inhibition, competitive inhibition, is relatively straightforward. In this case, the inhibitor binds to the active site of the enzyme in the same spot as the substrate, and therefore competes with the substrate for binding. Usually, this type of inhibitor looks like the substrate. This prevents the substrate from binding, which then lowers the Km. This is because if the inhibitor is competing with the substrate for binding, a higher concentration of substrate needs to be present to outcompete the inhibitor and achieve half of Vmax. However, once the substrate binds, chemistry proceeds as normal, so the Vmax does not change. If we used a Lineweaver-Burk plot to represent this, Lineweaver-Burk plots are really good for representing inhibition. The lines would have different slopes, but they would intersect on the y-axis. This would be because as the y-intercept is equal to 1 over Vmax, if Vmax does not change, they'll intercept it on that spot on the axis. However, the Km will change, so the slope will be different. One thing to note is that as the concentration of inhibitor increases, the slope increases, and the line that represents the enzyme in the presence of inhibitor will always be higher than the enzyme alone. The next type of inhibition is uncompetitive inhibition. In this type of inhibition, the inhibitor binds somewhere else on the enzyme, but it only binds the enzyme substrate complex, not the unbound enzyme. So as a result, the inhibitor distorts the active site, rendering the enzyme inactive and taking it temporarily out of commission. The result of the distorted active site is that it does chemistry less efficiently, leading to a decreased Vmax. But the Km decreases, the Km decreases, and this is because there are fewer enzyme molecules available. So if there are fewer enzyme molecules available, but the concentration of substrate stays the same, it's going to take a smaller concentration of substrate to achieve half Vmax because there are fewer active sites to bind to. This type of inhibition is represented by parallel lines on the Lineweaver-Burk plot because both the Vmax and the Km are affected by this type of inhibition. The last type of inhibition is mixed inhibition, which in some textbooks is called non-competitive. But we're going to use mixed because it's less confusing. In this case, the enzyme can bind either to the enzyme alone or to the enzyme substrate complex. Inhibition distorts the active site, which leads to a decreased Vmax, but the Km can either increase or decrease. The hallmark of this rarely seen method of inhibition is intersecting lines with the intersection point either to the right or the left of the y-axis. This is in contrast to competitive inhibition, which occurs on the y-axis. Here's a summary to help you remember the effects of each type of inhibitor. Note that the Vmax and Km are referred to as the apparent Vmax and Km because the altered values aren't the real values. Those aren't inherent to the enzyme substrate pair. They just appear to change based on the amount of inhibitor added. If we look back at those data that we had on the previous PowerPoint and then added an inhibitor, this is an example of what we might see. We could graph the double reciprocal plots of the enzyme both with and without inhibitor and get the following graph. One important thing to note is that the line with the enzyme in the presence of inhibitor, again, will always be above that of the enzyme without the inhibitor. Which type of inhibition is this? Pause, and why don't you find out? If you came up with competitive inhibition, you are correct. The two concentrations have different slopes, meaning they have different Kms, but they intersect at the y-axis, so they must have the same Km. So this is a hallmark of competitive inhibition. Inhibitors can either be reversible, where they pop back off the enzyme, or irreversible, where they make a covalent bond to the protein. And are permanently attached. Some examples of reversible inhibitor, which we'll talk more about next time, are reversible inhibitors of HIV protease, which is an enzyme found in the HIV virus. The substrate of HIV protease is at the top. It's a phenylalanine proline peptide bond. These two HIV drugs mimic the transition state of this compound, shown at the hydroxyls, shown in red, would represent the transition state of that carbonyl oxygen, which would be a deprotonated single bonded O in its transition state, which we'll talk about next lecture. But they don't possess an amide bond that can then be cut. So the enzyme will be stuck down to that transition state mimic and temporarily disabled. However, these inhibitors don't covalently bind the enzyme or covalently modify it, and so eventually they'll pop back off. Irreversible inhibition is when a stable covalent bond is formed between the inhibitor and the enzyme. For this enzyme, the inhibitor makes a covalent bond with a serine residue. This can be really useful for determining the mechanism of an enzyme. For instance, if you covalently modify an enzyme, and then the enzyme stops working, you can go back and crystallize the enzyme, see which amino acid is modified, and then that tells you which amino acid side chain is involved in catalysis.